right, our next speaker today is, if I'm informed well, Dr. Sebastian Murk now. Congratulations on a recent defense.
Thank you.
He's at Macquarie University, and he's going to talk about surface gravity and the information loss problem. So Sebastian, whenever you want, floor is yours.
Yeah, thank you for the kind introduction, and thank you to Eduardo and the organizing committee for orchestrating this conference. Before I get started with my talk, I just want to quickly point out that what I'm showing you today is the result of joint work with Robert Mann and Daniel Turner, who will be familiar to many of you. And I also want to make the usual disclaimer that because the time for contributor talks is so short, I will not be providing any mathematical derivations in this talk, but rather just going to try to show you what we found and put the results into context. That being said, if you are interested in the mathematical derivations, you can find them in this paper of the same name as my talk, which was recently published in Physical Review D, and all the mathematical details are in there. And I should also preface everything that I'm showing you today by saying that we work in the framework of semiclassical gravity. And if you've been with us yesterday in Daniel Turner's talk, we've seen exactly what that means actually. So I also, again, don't want to repeat every point. I would just want to stress here that really the hallmark feature of the semiclassical approaches, that is renormalized energy momentum tensor, is used to describe the entire matter content. So both the original collapsing matter and the produced quantum excitations. And then the dynamics of the collapsing matter is still described classically using a metric. And again, we try to keep things very generic. So we do not make any assumptions about the global structure of space-time or about the quantum state omega. We also don't make any a priori assumption about the energy conditions, so whether or not they're satisfied or violated, about singularities, or about the presence or absence of Hawking radiation. And one of the first, if not the first, to really take the semiclassical idea seriously was Stephen Hawking. And what he found was that if you take these quantum effects into account, then black holes will emit thermal radiation just like an ordinary black body does. And he predicted that due to these quantum effects, black holes will ultimately evaporate. And this prediction gave rise to a now very famous dilemma, which is the information loss paradox. And to illustrate why this is a problem, or why some people consider it to be a problem, imagine that you throw a bunch of things into a black hole, but then the black hole evaporates. And Stephen Hawking has shown this radiation that's emitted during this process is completely thermal. And thermality, he means that it's uncorrelated, so it cannot carry any information other than the mass and the temperature of the black hole. But from the mass and the temperature of the black hole alone, you cannot reconstruct what fell into the black hole. And this is a problem if you believe in quantum field theory, because quantum field theory is a unitary theory. And this really tells us that information should be preserved. But here it appears that once the black hole has evaporated completely, the information is gone. And now to backpedal a little bit, let's have a look at what actually the ingredients are that we need to formulate this paradox in the semiclassical framework. And the first ingredient that we need is the formation of a transient trap region in finite time of a distant observer. And so this is needed to simply to provide the scattering-like setting that we use to describe the states, and not just the states, but also the alleged quantum information content that they're associated with before and after the evaporation process. The second ingredient that we need is an event horizon. And I want to stretch here that you really need an event horizon. Any quasi-local notion of horizon is not good enough because it's observer dependent. And you really need an event horizon to give an objective observer independent significance for tracing out degrees of freedom of the black hole. And then lastly, the radiation should be thermal in character. And this is just needed to ensure that during the evaporation process, the correlations between the inside and the outside of the black hole cannot be restored in this radiation. And in some formulations, you find additional assumptions that are being made. But these are the three assumptions that are really absolutely necessary for any formulation of the information loss problem. Now, the question is, what are actually the physical consequences of having these requirements realized in nature? And here it's important to keep in mind that event horizons are not physically observable, which means that if we want to concern ourselves with objects that we can, in principle, observe, then we have to work with quasi-local motions, such as the apparent horizon. However, having said that, we know that for an evaporating black hole, the existence of an event horizon actually implies the formation of an apparent horizon. So if we need an event horizon to formulate a paradox, then actually we can't get around also having an apparent horizon. And so the first two ingredients that I showed you in the paradox, we can actually formulate as the formation of a regular apparent horizon in finite time of a distant observer. And then we can ask, assuming that those two ingredients are realized in nature, what can we say about the third one? Is that also a possibility or not? And it turns out that this simple assumption here, which seems innocent, that you have a regular apparent horizon that forms in finite time of a distant observer, is actually strong enough to constrain the near horizon geometry almost uniquely and to prescribe a unique black hole formation scenario. Now we work in spherical symmetry. So that means we use this line element that you see here, which is the most generic way to write or to describe a spherically symmetric geometry, where this function f here is defined as 1 minus c over r. C, or more precisely c half, is just the Misner sharp mass. So this is a notion of the gravitational energy that's enclosed within a sphere of radius r. And it's very convenient because by its very definition, it's invariant. So it'll be the same across different coordinate systems. And then this other function that pops up in the line element here, h, is essentially just an integrating factor that tells you how to transform between different coordinate systems. So for example, between Schwarzschild and advanced null coordinates, so TR and VR coordinates. And in spherical symmetry, you can write the Einstein equations in this very compact form, where rather than working with energy momentum tensor components, we use these what we call effective energy momentum tensor components. So these are just the standard components rescaled by some factors of e to the power of minus h. And the reason for doing this is that it's very convenient because you can see now that there's only one equation where both c and h simultaneously appear. Because of this rescaling, the other factors of e to the power of minus h and h have canceled. So c and h simultaneously appear only in one equation. And what that means is we can now solve the third equation independently for h, solve the first one independently for c, and then the second equation will give you a consistency condition that governs the dynamic evolution of your black hole, because it's the time derivative of this function c, which is related to the Misner sharp mass. And of course, we can also write our curvature scalars in terms of these effective energy momentum tensor components. So it's really very convenient to work with those in spherical symmetry. And it turns out that there are actually only two dynamic classes of solutions that are self-consistent. And you can characterize those by the scaling behavior of these energy momentum tensor components close to the horizon. And what you'll find is that as you approach the horizon, they will scale as some function of time times f to the power of k, where f is the function that we've defined here that's related to the Misner sharp mass. But then it turns out k can only take on two distinct values, namely k0 and k1. So we refer to those two classes as k0 and k1 solutions. And both of them violate the null energy condition near the horizon. And I should stretch here that this is not an assumption. This is actually an immediate consequence that follows from the requirement that an apparent horizon forms, or that a regular apparent horizon forms in finite time of a distant observer. And now what you see here, this is what the two classes of solutions look like explicitly. For K1 solution, there's only one unique one that's self-consistent, which is why the singular form's used here. And here they are written, or they're written as series expansions in terms of x, where x is the aerial radius minus the horizon radius. So this is the coordinate distance from the horizon. And it turns out that you need both of these classes to describe the evolution of black holes. And more precisely, we know that at the instant of their formation, physical black holes are described by this unique K1 solution. And then immediately after the formation, the behavior switches to that of a K0 solution, and it'll remain a K0 solution for the rest of its lifetime. And again, both of those violate the null energy condition near the horizon. And I should also mention the transition between those two classes is continuous. And what makes this smooth transition possible is actually that for the K1 solution, the null energy condition is violated only outside of the apparent horizon. So for some R greater than RG, but for K0 solutions, it's actually also violated up to some R smaller than RG. And this enables this continuous transition between the two classes of solutions. So now we've covered all the relevant context that we need to look at surface gravity. And surface gravity is unambiguously defined only in stationary spacetimes, where we have this relation to the Hawking temperature of a stationary black hole, and this is valid for an observer sitting at infinity. And am I down to 2 minutes?
Not yet.
Not yet. Okay, good.
Okay, 2 minutes and 10 seconds.
Okay, awesome. Thank you. So in the stationary case, there are actually several related definitions of surface gravity, and broadly speaking, you can categorize them. You can put them into categories. They're either related to the inner affinity of null geodesics on the horizon, so this is the definition with the killing vector field, or they're related to the peeling off properties of null geodesics near the horizon. So here they're defined as the linear coefficient in the Taylor series of the expansion of a radial null geodesic. Now, in general dynamical spacetimes, the problem is that we no longer have an asymptotically time-like killing vector, but of course there are still different proposals to generalize surface gravity to dynamical scenarios. And again, they fall into two categories, namely peeling or Kodama surface gravity. And it turns out that for slowly evolving horizons that have properties close to their classical counterparts, these two are actually indistinguishable. But what we've shown in our paper is that this similarity actually completely breaks down for the two self-consistent classes of solutions that I've shown earlier. And the way we can see this is by simply evaluating the expression for the peeling surface gravity. So this is it written in terms of the metric functions h and c. And if you look at, for example, the K0 solutions, but it's true for both classes of solutions, you will see pretty quickly that this diverges because you're evaluating it at Rg. So here you have a logarithm of 0, and that'll already diverge. Maybe another way of seeing it is that in comparison to the stationary expression, you have this non-zero constant term, and you also get a square root term in the expansion of the radial null geodesic. And just for completeness, I should also mention that initially the peeling surface gravity was defined using Panlev Gilson coordinate. But again, these are discordant. You get 0 for one. The other one can be non-zero. It can be 0 or infinite. So even definitions that are supposedly the same do not agree with each other. And now the second class, the Kodama surface gravity. So this is the one defined using the Kodama vector field and its covariant derivatives. Here you find that it's 0 at the formation of a black hole, so for the K0 solution. And after that, you can never approach the static value because it would contradict semiclassical results, established semiclassical results. And since I'm out of time, I will leave you with this one sentence summary, which is that we learned if semiclassical gravity is valid, and we've realized the first two ingredients that we need to formalize the paradox, then it's impossible to also realize the third one, namely the thermal character of the radiation. And again, if you're interested in mathematical details, this is the Physical Review D paper. And if you want even more details, this is our review that was recently published in International Journal of Modern Physics D. And also, of course, both of them are available on the archive. And I'll stop here and maybe we can have a question or two. Thank you.
Okay, thank you, Sebastian. All right, we were 1 minute over the time, so we have time for one question, perhaps a very short one. If you have a longer one, maybe save it for the end of the session. Does anybody have a quick question? All right, I don't see any hands. So if you want to, if you could, I mean, again, stay around for the end of the session. If not, we can continue in Slack. Thank you very much, Sebastian.
Thank you for having me.